For the rest of the term, we're going to be studying not just one differential equation at a time, but rather what are called systems of differential equations. Those are like systems of linear equations. They have to be solved simultaneously, in other words, not just one at a time. So, how does a system look when you write it down? Well, there's still, since we're going to be talking about systems of ordinary differential equations, there still will be only one independent variable, but there will be several dependent variables. So I'm going to call, let's say, 2. So the dependent variables are going to be, I'll call them x and y, and then a first-order system, something involving just first derivatives, will look like this. On the left-hand side will be x prime, dx dt, in other words. On the right-hand side will be the dependent variables, and then also the independent variables. I'll indicate that separated off from the others by putting a semicolon there. In the same way, y prime, the derivative of y with respect to t, will be some other function of x, y, and the... So let's write down explicitly that x and y are dependent variables. And what they depend upon is the independent variable t, time. A system like this is going to be called first order. And we're going to consider basically only first order systems for a secret reason, which I'll explain at the end of the period. First order, so this is a first order system, meaning that the only kind of derivatives which appear are first derivatives. So x prime is dx dt and so on. Now there's still more terminology. Of course, practically all the equations after the term started, virtually all the equations we've been considering are linear equations, so it must be true that linear systems are the best kind, and boy, they certainly are. So when are we going to call a system linear? I think in the beginning you should learn a little terminology before we launch in and actually try to start to solve these things. A linear system, well, the x and y, the dependent variables, must occur linearly. So in other words, it must look like this. ax plus by. Now the t can be a mess, and so I'll throw in an extra function of t there, and y prime will be some other linear combination of x and y, plus some other messy function of t. But even the a, b, c, d are allowed to be functions of t. They could be 1 over t cubed or sine t or something like that. So I have to distinguish those cases. The case where a, b, and c, d are constants, that I'll call, well, it doesn't have a, there are different things you call it. We'll simply call it a constant coefficient system. A system with constant coefficients would probably be better English. On the other hand, A, B, C, D, the system will still be called linear if these are functions of t. Can be functions of t. Can also be functions of t. So it would be a perfectly good linear system to have x prime equals tx plus sine t times y plus e to the minus t squared. You'd never see something like that, but it's okay. It's okay. What else do you need to know? Well, what would a homogeneous system be? Homogeneous system is one without these extra guys. That doesn't mean there's no t in it. There could be t in the a, b, c, and d, but these terms with no x and y in them must not occur. So a homogeneous, linear homogeneous, and that's the kind we're going to start studying first. In the same way, when we studied higher order equations, we studied first homogeneous. You had to know how to solve those first, and then you could learn how to solve the more general kind. So linear homogeneous means that R1 is 0 and R2 is 0 for all time. They're identically zero. They're not there. You don't see them. Have I left anything out? Yes, the initial conditions. Since that's quite general, let's talk about what would initial conditions look like. Well, in a general way, the reason you have to have initial conditions is to get values for the arbitrary constants that appear in the solution. So the question is, how many arbitrary constants are going to appear in the solution to these equations? Well, I'll give you the answer, 2. The number of arbitrary constants that appear is the total order of the system. For example, if this were a second derivative and this were a first derivative, I would expect 3 arbitrary constants in the system, and it would be called, because the sum of 2 and 1 makes 3. So you must have as many initial conditions as you have arbitrary constants in the solution. And that, of course, explains when we studied second-order equations, we had to have 2 initial conditions. I had to specify the initial starting point and the initial velocity. And the reason we had to have 2 conditions was because the general solution had 2 arbitrary constants in it. Well, the same thing happens here, but the answer is it's more natural. The conditions here are more natural. I don't have to specify the velocity. Why not? Well, because an initial condition, of course, would want me to say what the starting value of x is, some number, and it will also want to know what the starting value of y is at that same point. Well, there are my 2 conditions. And since this is going to have 2 arbitrary constants in it, it's these initial conditions that will satisfy those 2. The arbitrary constants will have to be picked so as to satisfy those initial conditions. So in some sense, the giving of initial conditions for a system is a more natural activity than giving the initial conditions of a second-order system. You don't have to be the least bit clever about it. Anybody would give these 2 numbers, whereas somebody faced with a second-order system might scratch his head. And in fact, there are different other kinds of conditions which you can, there are boundary conditions you learned a little bit about instead of initial conditions for a second-order equation. Okay. I can't think of any more general terminology. So it sounds like we're going to actually have to get to work. Okay, let's get to work. So I want to set up a system and solve it. And since one of the things in this course is supposed to be simple modeling, it should be a system that models something. In general, the kinds of models we're going to use when we study systems are the same ones we use in studying just first-order equations. Mixing, radioactive decay, temperature, the motion of temperature, heat conduction, in other words, diffusion. I've given you a diffusion problem for your first homework on this subject. What else did we do? Well, that's all I can think of for the moment, but I'm sure others will occur to me. Now, when out of those ideas, those physical ideas, when are we going to get a system? The answer is whenever there's 2 of something that there was only 1 of before. So, for example, if I have mixing with 2 tanks where the fluid goes like that and the fluid, say you want to have a big tank and a little tank here and you want to put some stuff into the little tank so that it'll get mixed with the big tank without having to climb a big ladder and stop and drop the stuff in, that will require 2 tanks, the concentration of the substance in each tank, and therefore that will require a system of equations rather than just 1. Or, to give something closer to home, suppose, closer to this blackboard anyway, suppose, you got a da-da-da-da-da-da, don't groan, at least not audibly, something that looks like that, and next to it, okay, put an EMF there. Okay, that's just a first order. That just leads to a single first order equation. But suppose it's a 2-loop circuit. Ooh. Yeah. Now I need a pair of equations. This is now, each of these loops gives a first order differential equation, but they have to be solved simultaneously to find the current or the charges on the condensers. And if I want a system of 3 equations, throw in another loop. Now, suppose I put in a coil instead. What's this going to lead? This is going to give me a system of 3 equations, of which this will be first order, and this will be second order because it's got a coil. You're up to that, right? You've had coils, inductance. Good. Okay. So the whole thing is going to count as first order, second order. You have to add, to find out how complicated it is, you have to add up the orders. That's 1 and 1 and 2 makes, this is really fourth order stuff that we're talking about here. We can expect it to be a little complicated. All right, well now let's take a modest little problem. So I'm going to return to a problem we considered earlier in the problem of heat conduction. I've forgotten whether it was on the problem set or I did in class, but anyway, I'm choosing it because it leads to something we'll be able to solve, and because it illustrates how to add a little sophistication to something that was unsophisticated before. So, a pot of water, external temperature TE of T. I'm talking about the temperature of something, and what I'm talking about the temperature of will be an egg that is cooking inside, but an egg with the difference. This egg is not homogeneous inside. Instead, it has a white and it has a yolk in the middle. In other words, it's a real egg, not a phony egg. It's a small pot. Or it's an ostrich egg. Okay, that's the yolk. The yolk is contained in a little membrane inside, and there are little yucky things that hold it in position. And we're going to let the temperature of the yolk, if you can see at the back of the room, be T1 is the temperature of the yolk. The temperature of the white, which we'll assume is uniform, is going to be T2. And then, oh, that's the water bath, isn't it? Okay. So the temperature of the white is T2. And then the temperature of the external water bath. So in other words, the reason for separating, introducing 2 variables instead of just the 1 variable for the overall temperature of the egg we had is because egg white is liquid pure protein, more or less, and the T1, the yolk, has a lot of fat and cholesterol and other stuff like that, which is supposed to be bad for you. It certainly has different conducting. It's liquid at the beginning at any rate, but it has certainly different constants of conductivity than the egg white would. And the shell, what conduction of heat through the shell of the egg would be different from the conduction of heat through the membrane that keeps the yolk together. So it's quite reasonable to consider that the white and the yolk will be at different temperatures and will have different conductivity properties. So I'm going to use Newton's laws, but with this further refinement, in other words, introducing 2 temperatures, whereas before we only had 1 temperature. So let's use Newton's law. Let's see. So the question is, how does T1, the temperature of the yolk, vary with time? Well, the yolk is getting all its heat from the white. And therefore, Newton's law of conduction will be some constant of conductivity for the yolk times T2 minus T1. The yolk doesn't know anything about the external temperature of the water bath. It's completely surrounded, snug, and secure within itself. But how about the temperature of the egg white? That gets heat from, or gives heat to 2 sources, from the external water and also from the internal yolk inside. So you have to take account of both of those. Its conduction of the heat through that membrane, we'll use the same A, so that's going to be A times T1 minus T2. Remember, the order in which you have to write these is governed by the outside, the yolk is outside to the white, and therefore that has to come first when I write it in order that A be a positive constant. But it's also getting heat from the water bath, and presumably the conductivity through the shell is different from what it is through this membrane around the yolk. So I'm going to call that by a different constant. So this is the conductivity through the shell into the white, and that's going to be T, the external temperature, minus the temperature of the egg white. So here I have a system of equations because I want to make two dependent variables by refining the original problem. Okay, now you always have to write a system in standard form to solve it. You'll see the left-hand side will give the dependent variables in a certain order. In this case, the temperature of the yolk and then the temperature of the white. The law is that in order not to make mistakes, and it's a very frequent source of error, so learn from the beginning not to do this. You must write the variables on the right-hand side in the same order, left to right, in which they occur top to bottom here. So in other words, this is not a good way to leave that. This is the first attempt at writing the system, but the final version should look like this. T1 prime, I won't bother writing dt dt, is equal to T1 must come first. So minus A times T1 minus plus A times T2. And the same law for the second one. It must come in the same order. Now, the coefficient of T1, that's easy. That's A times T1. The coefficient of T2 is minus A minus B. So minus A plus B times T2, but I'm not done yet. There's still this external temperature I must put into the equation. Now, that's not a variable. This is some given function of T, and what the function of T is, of course, depends upon what the problem is. So that, for example, what might be some possibilities? Well, suppose, for example, the problem were I wanted to coddle the egg. I think there's a generation gap here. That how many of you know what a coddled egg is? How many of you don't know? I think there's well, I'm just saying my daughter didn't know. I mentioned it to her. I said, I think I'm going to do a coddled egg tomorrow in class. And she said, what's that? And then so I said, oh, cuddled egg? She said, why would someone cuddle an egg? So I said, coddle. And she said, oh, you mean like a person? Like what you do to somebody you like or don't like, or I don't know, whatever. So I thought a while and said, yeah, more like that. Anyway, so for the enrichment of your cooking skills, to coddle an egg, it's considered it's considered to produce a better quality product than boiling an egg. That's why people do it. You heat up the water to boiling, and then the egg should be at room temperature, and then you carefully lower the egg into the water, and you turn off the heat so the water bath cools exponentially while the egg inside is rising in temperature, and then you wait 4 minutes or 6 minutes or whatever and take it out and you have a perfect egg. Okay, so for coddling, spelt so, what will the external temperature be? Well, it starts out at time 0 at 100 degrees centigrade because the water is supposed to be boiling. The reason you have it boiling is so that for calibration, so that you can know what temperature it is without having to use a thermometer, unless you're on Pikes Peak or someplace. So it starts out at 100 degrees, and after that, since the light is off, it cools exponentially, because that's another law. So you only have to know what K is for your particular pot, and you'll be able to solve the coddled egg problem. In other words, so you'll then know how be able to solve these equations and know how the temperature rises. I'm going to solve a different problem because I don't want to have to deal with this inhomogeneous term. So let's use as a different problem. A person cooks an egg, coddles the egg by the first process, decides the egg is done, let's say hard-boiled, and then you're supposed to drop a hard-boiled egg into cold water, not just to cool it, but also because I think it prevents that dark thing from forming that looks sort of unattractive. So let's ice bath. But the only reason for dropping the egg into an ice bath is so that you can have a homogeneous equation to solve. And since this is the first system we're going to solve, let's make life easy for ourselves. Now, all my work in preparing this example, and it took considerably longer time than actually solving the problem, was in picking values for A and B, which would make everything come out nice. That's harder than it looks. So the values we're going to use, which make no physical sense whatever, but A equals 2 and B equals 3. These are called nice numbers. So what's the equation? What's the system? Can somebody read it off for me? It's T1 prime equals, what is it? The A is, minus 2T1 plus 2T2, right? 2T2, that's good. Minus 2T1 plus 2T2. T2 prime is, what is that? I think this is 2T1, and the other one is what? A minus A plus B, so minus 5. This is a system. Now, on Wednesday, I will teach you a fancy way of solving this. But to be honest, the fancy way will take roughly about as long as the way I'm going to do it now. The main reason for doing it is that it introduces new vocabulary, which everyone wants you to have. And also, a more important reason, it gives more insight into the solution than this method. This method just produces the answer. But you want insight also, and that's just as important. But for now, let's use a method which always works and which in 40 years after you've forgotten all other fancy methods will still be available to you because it's a method you can figure out yourself. You don't have to remember anything. The method is to eliminate one of the dependent variables. It's just the way you solve systems of linear equations in general if you aren't doing something fancy with determinants and matrices. If you just eliminate variables. So we're going to eliminate one of these variables. Let's eliminate T2. You could also eliminate T1. The main thing is eliminate one of them, so you'll have just one left to work with. Now, how do I eliminate T2? Beg pardon? Is something wrong? Somebody who thinks something's wrong, raise his hand. No? Why do I want to get rid of T1? I'm sorry? Well, I can add them, but on the left-hand side, I'll have T1 prime plus T2 prime. What good is that? I think you want to do it my way. Solve for T2 in terms of T1. So that's going to be T1 prime plus 2T1 divided by 2. Now, take that and substitute it into the second equation. Wherever you see a T2, put that in, and what you'll be left with is something just in T1. To be honest, I don't know any other good way of doing this. There is a fancy method which I think is talked about in your book, which leads to extraneous solutions and so on, but you don't want to know about that. This will work for simple linear equations with constant coefficients always. Okay, so substitute in, what do I do? Now, just here, I do not advise doing this mentally. It's too easy to make a mistake. So here, I will do it carefully writing everything out just as you would. So T1 prime plus 2T1 over 2 prime equals 2T1 minus 5T2 minus 5 T1 prime plus 2T1 over 2. Okay? I took that and substituted into this equation. Now, I don't like those 2's. Let's get rid of them by multiplying. So this will become 4, and this will become, go 2. And now write this out. What is this when you look at it? This is what order is this? This is an equation just in T1. It has constant coefficients. And what is its order? Its order is 2, right? Because T1 prime. In other words, I can eliminate T2 okay, but the equation that I'm going to get is no longer a first order, it becomes a second order differential equation. And that's a basic law that if you have a system, even if you have a system of more equations, 3 or 4 or whatever, the law is that after you do the elimination successfully and end up with a single equation, normally the order of that equation will be the sum of the orders of the things you started with. So 2 first-order equations will always produce a second-order equation in just one dependent variable. 3 will produce a third-order equation, and so on. So you trade one complexity for another. You trade the complexity of having to deal with 2 equations simultaneously instead of just one for the complexity of having to deal with a single higher-order equation, which is more trouble to solve. It's like all mathematical problems, unless you're very lucky, if you push them down one way, really simple now, they just pop up someplace else. You say, oh, I didn't save anything after all. That's the law of conservation of mathematical difficulty. So you saw that even with the Laplace transform. In the beginning it looks great. Hey, got these tables, take the equation, horrible to solve, take a subtransform, trivial to solve for capital Y. Uh-oh, now I have to find the inverse Laplace transform, and suddenly all the work is there. Partial fractions, funny formulas, and so on. So it's very hard in mathematics to get away with something. It happens now and then, and everybody cheers. Okay, so let's write this. We have to write this out now in the form in which it looks like an equation we can actually solve. Just be careful. Now it's all right to use the method by which you collect terms. So there's a term. There's only one term involving T1 double prime. It's the one that comes from here. How about the terms in T1 prime? There's a 2. Here there is minus 5 T1 prime. If I put that on the other side, it makes plus 5 T1 prime, plus this 2 makes 7 T1 prime. And how many T1s are there? Well, none on the left-hand side. On the right-hand side, I have 4 here, minus 10. 4 minus 10 is negative 6. Negative 6 T1 put on this left-hand side, the way we want to do, makes plus 6 T1. There are no inhomogeneous terms, so that's equal 0. If I had gotten a negative number for one of these coefficients, I would instantly know I had made a mistake. Why? Why must those numbers come out to be positive? It's because the equation the system must be, fill in with one word, stable. And why is this system must be stable? In other words, the long-term solutions must be 0, must all go to 0, whatever they are. Why is that? Well, because you're putting the egg into an ice bath. Or because we know, because the egg was living, but after it's hard-boiled, it's dead, and therefore dead systems are stable. That's not a good reason, but it's... is, so to speak, the real one. It's clear anyway that all solutions must tend to 0 physically. That's obvious. And therefore, we want the differential equation must have the same property, and that means that its coefficients must be positive. All its coefficients must be positive. If this weren't there, I'd get oscillating solutions which wouldn't go to 0. That's physically impossible from this egg. Okay, so now the rest is just solving. So the characteristic equation, if you can remember way, way back in prehistoric times when we were solving these equations, characteristic equation is this. And what you want to do is factor it, so it factors into R. This is where all the work was, getting those numbers so that this would factor. Okay, so it's R plus 1 times R plus 6. And so the solutions are, the roots are R equals -1. I'm just making marks on the board, but you've done this often enough, you know what I'm talking about. So the characteristic roots are those two numbers, and therefore the solution is, I could write down immediately with its arbitrary constant as C1 times e to the -t plus C2 times e to the -6t. Ta-da! Now, I got to get T2. The first worry is T2 is going to give me 2 more arbitrary constants. It better not. This system is only allowed to have 2 arbitrary constants in its solution because that's the initial conditions we're giving it. By the way, I forgot to give initial conditions. Let's give initial conditions. Let's say the initial temperature of the yolk when it's put in the ice bath is 40 degrees centigrade Celsius. And T2, let's say, the white should be a little hotter because the yolk is always cooler than the white for a soft-boiled egg, I don't know, or hard-boiled egg if it hasn't been chilled in too long. So let's make this 45. Realistic numbers. Okay, now the thing not to do is to say, hey, I found T1. Okay, I'll find T2 by the same procedure. I'll go through the whole thing, eliminate T1 instead, then I'll end up with an equation in T2, and I'll solve that, and I'll get T2 equals blah, 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 blah. That's no good, A, because you're working too hard, and B, because you're going to get 2 more arbitrary constants unrelated to these 2, and that's no good. Because the correct solution only has 2 constants in it, not 4. So that procedure is wrong. You must calculate T2 from the T1 that you found, and that's the equation which does it. That's the one we have to have. And where's the chalk? Ah, yes. Maybe I can have a little thing you just carry us around with you. Just wondering. Okay. Ta-da. That's the relation between T2 and T1. Or if you don't like, you can always go back to either one of these equations will express T2 in terms of T1 for you. It doesn't matter. Whichever one you use, you have to, however you do it, that's the way you must calculate T2. So what is it? So T2 is calculated from that pink box. So it is 1/2 of T1 prime plus T1. All right. 1/2 of T1 prime plus T1. All right, now, if I take the derivative of this, I get minus C1 times the exponential. So the coefficient is minus C1. Take half of that. That's minus 1/2 C1. And add it to T1. So minus 1/2 C1 plus C1 gives me 1/2 C1. And here, I take the derivative, it's minus 6C2. Take half of that, minus 3C2, and add this C2 to it. Minus 3 plus 1 makes minus 2. That's T2, and notice it uses the same arbitrary constants that T1 uses. So we end up with just 2. Because we calculated T2 from that formula, or from the equation, which is equivalent to it, not from scratch. Well, we haven't put in the initial conditions yet, but that's easy to do. Everybody, when working with exponentials, of course, you always want the initial conditions to be when t is equal to 0, because that makes all the exponentials 1, and you don't have to worry about them. But this you know. So if I put in the initial conditions, at time 0, t1 has the value 40. So 40 should be equal to c1 plus c2. And the other equation will say that 45 is equal to 1/2 c1 minus 2 c2. Now we're supposed to solve these. Well, this is called solving simultaneous linear equations. We could use Kramer's rule, inverse matrices, but why don't we just eliminate? So let me see. So this is, if I multiply by 45, so multiply by 2. So you get 90 equals C1 minus 4C2. Then subtract this guy from that guy. So 40 taken from 90 makes 50. And C1 taken from C1, because I multiply by 2, makes 0. And C2 taken from minus 4C2, that makes minus 5C2, I guess. So I seem to get that C2 is equal to negative 10. And if C2 is negative 10, then this must be, C1 must be 50. Now, there are two ways of checking the answer. One is to plug it into the equations. The other is to peek. Yes, that's right. Okay. So the final answer is, in other words, you put a 50 here, 25 there, negative 10 here, and 20, positive 20 there, and thus gives the answer to the problem. It tells you, in other words, how the temperature of the yolk varies with time and how the temperature of the white varies with time. Now, as I said, we're going to learn a slick way of doing this problem, or at least a very different way of doing the same problem next time. But let's put that on ice for the moment. And instead, I'd like to spend the rest of the period doing for systems, first-order systems, the same thing that I did for you the very first day of the term. Remember, I walked in assuming that you knew how to separate variables. And the first day of the term, I did not talk to you about how to solve fancier equations by fancier methods. I instead talked to you about the geometric significance, what the geometric meaning of a single first-order equation was, and how that geometric meaning enabled you to solve it numerically. And we spent a little while working on such problems because nowadays with computers, it's really important that you get a feeling for what these things mean as opposed to just algorithms for solving them. Yeah, as I say, most differential equations, especially systems, are likely to be solved by a computer anyway. You have to be the guiding genius which interprets the answers and can see when mistakes are being made, stuff like that. So the problem is, therefore, what is the meaning of this system? Well, you're not going to get anywhere interpreting it geometrically unless you get rid of that t on the right-hand side. And the only way of getting rid of the t is to declare that it's not there. So I hereby declare that I will only consider, for the rest of the period, that's only 10 minutes, systems in which no t appears explicitly on the right-hand side, because I don't know what to do if it does appear. We have a word for these. Remember what the first-order word was? It was a first-order equation where there was no t explicitly on the right-hand side. We called it, anybody remember? Just curious. Autonomous, right? This is an autonomous system. It's not a linear system because these are messy functions. This could be x times y, or x squared minus 3y squared divided by x sine of x plus y. It could be a mess. Definitely not linear, but autonomous means no t. T means the independent variable appears on the right-hand side. Of course, it's there. It's buried in the dx dt and dy dt, but it's not on the right-hand side. No t appears on the right-hand side. Now, because no t appears on the right-hand side, I can now draw a picture of this. But in order to explain, let's see, what does a solution look like? I never even talked about what a solution was, did I? Gad. Okay, well, pretend that this, immediately after I talked about that, I talked about this. What is a solution? Well, a solution is, maybe you took it for granted, is a pair of functions x of t, y of t, which when you plug it in, it satisfies the equation. And so what else is new? So solution is x equals x of t, y equals y of t. Well, if I draw a picture of that, what would it look like? Okay, this is where your previous knowledge of physics at above all of 1802 and maybe of 1801, if you learned this in high school. What is x equals x of t and y equals y of t? How do you draw a picture of that? What does it represent? A curve, and in what chapter of the book, what will be the title of the chapter of the calculus book in which that is discussed? Parametric equations. This is a parametrized curve. So we know what the solution looks like. A solution is a parametrized curve. And what does a parametrized curve look like? Well, it travels and in a certain direction. Okay, that's enough. Why do I have several of those curves? Well, because I have several solutions. In fact, given any initial starting point, there's a solution that goes through it. So I'll put in possible starting points. Now you can do this on the computer screen with a little program you'll have, one of the visuals you'll have, it's being made right now. You put down, start a point, put down a click, and then it just draws the curve passing through that point. Didn't we do this earlier in the term? Yes, but there's a difference now, which I'll explain. So these are various possible starting points at time 0 for this solution, and then you see what happens to it afterwards. In fact, through every point in the plane will pass a solution curve, parameterized curve. Okay. Now, what's then the representation of this? Well, what's the meaning of x prime of t and y prime of t? I'm not going to worry for the moment about the right-hand side. What does this mean by itself? If this is the curve, the parameterized motion, then this represents its velocity vector. It's the velocity of the solution at time t. If I think of the solution as being a parameterized motion, it has at each point, not merely all I've drawn here is the trace, the path of the motion. This hasn't indicated how fast it was going. One solution might go, and another one might go, has a velocity. And that velocity changes from point to point. It changes both direction. Well, we know its direction at each point. That's tangent. What I cannot tell is the speed. From this picture, I cannot tell what the speed was. Okay, too bad. Now, what is then the meaning of the system? What the system does, it prescribes at each point the velocity vector. If you tell me what the point x, y is in the plane, then these equations give you the velocity vector at that point. And therefore, what I end up with, the system, is what you call in physics and what you call in 1802 a velocity field. So at each point, there's a certain vector. The vector is always tangent to the solution curve through there, but I cannot predict from just this picture what its length will be, because at some points it might be going slow. The solution might be going slowly. In other words, the plane is filled up with these guys. Stop me. Not enough here. So on and so on. So we can say a system of first-order equations, ODEs, of two first-order equations, autonomous, because there must be no t on the right-hand side, is equal to a velocity field. A field of velocity vectors, the plane covered with velocity vectors, and a solution is a curve, a parametrized curve with the right velocity everywhere. Now, there obviously must be a connection between that and the direction fields we studied at the beginning of the term. And there is. It's a very important connection. It's too important to talk about in -1 minute. So when we need it, I'll have to spend some time talking about it then.